And welcome back to another LeetCode problem. We're going to continue with our bit manipulation problems and the LeetCode IO 150 list. We're going to look at sum of two integers next. So what do we have here? Well, we have LeetCode 371, sum of two integers, a medium problem. We're given two integers a and b, and we should return the sum of these two integers without choosing the operators plus or minus. Now, the constraints are that we can have negative and positive numbers. And here we see some examples. Well, obviously the inputs are decimal numbers and the output is also going to be decimal numbers. So you can clearly see that it's just an addition. Well, how do we approach this if we can't really use addition and subtraction? Well, we'll have to use bit manipulation. And if you remember how you can do addition of single bits, let's have a quick look. Where are we? Yeah. So if we have two numbers, and let's say we have them in, I guess, binary form, right? If we have the number 0 and 1, and we want to do an addition, let's say with with the number 1, 1. So if we want to add them in binary, well, we would add the least significance bits. Of course, that's going to be 0, and we will have a carry of 1 here. And then in the next step, we have to compute the sum of the carry plus the digits of the first two numbers at that position, which is also going to be, well, 0 and another carry. Now, there's nothing else here. So what that means is that our result becomes 1, 1, 0. And if we think about this, we have to essentially figure out how to compute the carry and then how to do the addition. And this can be done in two steps. So you split this up into the computation of the carry, and that is nothing but doing an AND operation. So if we have well, I guess the AND operation, and if we just draw the addition table in binary, 0 and 0 is 0, 0 and 1 is also 0. Oops. It's an AND, it's not really an addition, the AND operation. And same here, only when both are set to 1 do we get the value 1. So for the carry, we're going to use the AND operation, right? So that's what we're going to use here. And well, for computing the sum of two digits, we will use another operation. Namely, we will use the XOR operation. If 0, 1, 0, 1. And as you might remember, A XOR B is exactly 1 when only one of the two, A or B, is set to 1, and it's 0 in the other cases. So if we have a 0, 1, the result would be 1. If we 0, 1 XOR, well, if we have two digits 0 and 1 and we XOR them, that would give us a 1. But of course, then we're also going to XOR it again with the carry, and that is why we get the 0 here. So let me just write this. So what we'll do is we will have A XOR B XOR carry, right? That's going to be our digit value. And then we have to compute the carry. And the carry, as we've already seen, is simply A and B. However, if we compute A and B, the value is 1, but we have to left shift it by 1 position. So we can do this as well with a little trick. Well, not a trick, just an operator. In Python, it's just double smaller signs. That means shift to the left, right? So that will be the carry calculation. All right, so now we have we have broken down the addition into 2 steps for 2 digits. Well, but we have to do this for all digits that we might have in a number. So say if we have the number, let's say 1, 0, 1, 1, and on the other hand, we have the number 0, 1, 1, 0, right? And maybe there's another 0 here in front. So how can we do that in this case? Well, what is really cool is that we can use these operations regardless of how many digits we have in A and B. It will always work. So if we did this addition in all of the spaces, let's say, okay, so this is our A, this is our B, and this is going to be our carry. Well, in the beginning, well, actually, let's compute the carry for this case. So all we need to do is we need to compute A and B, and then shift it by 1 bit. So let's do that. The first bit is 0 and 0, so the last bit of the carry is going to be 0. Then we actually have a matching 1 in these positions. So A and B is 1 here. Next, we have 0, and another 0, and another 0. So A and B are only the same at in the second bit. And now we have to left shift the carry, so that means we add 1 bit here. Right. So now let's compute the digit values for A and for B. And we can do that simply by saying, well, our new A is going to be A XOR B. So let's do that now. And what do we get? If we compute A XOR B, we get 1. Because 0, this 1 is different from this 0. Then we get a 0 because they're all the same here. And then we get a 1 in this place, a 1 in that place, and a 0 here. Right, so now what we need to do is we need to combine the carry that we already have. Here we have the carry with our new value of A, because A contains the addition of A and B, but without any carries. So how can we combine them? Well, we can just AND them, right? What we would do is, oh, no, I misspoke. So what we do now is, well, the realization is we have to now add this value to that value, right? We already left shifted this. And we know in our manual calculation, a carryover means we're adding it to the addition in the next digit. So that's all we need to do. We just need to say, well, our B becomes now the carry, and we perform exactly the same steps as before. And we can do this for however as long it takes to reach that B is 0. And that's essentially the entire algorithm. So why don't we just go and implement this? And we will have to take care of negative numbers as well, but I'm going to show you this in a moment. Right, so, well, we're going to have our variables A and B. And like I said, we're going to use B as the carry. And, well, so we're going to iterate until B is actually 0. So now we're going to compute the carry, and it's nothing but A and B, like I said. And we have to shift it to the left. Now we compute A, and A is A XOR B. So that computes where all the bits are different. So this is addition without carry. And how do we get the carry in here? Well, we turn it into another addition problem. So we just say A is equal to our carry. And now we're going to loop. So we're going to now add the carry to our A in the next iteration of the loop. And in the end, we would just return A. So let's see what happens when we run this. It passes. And what happens when I submit this? It says time limit exceeded. Well, why could that be? Well, maybe it is because, on which we're on -1 and b equals 1. So that means that we actually have a problem with the sign. And so we need to add that to our code. And the way to do that in Python as well, we have to define what is the range of valid bits. So that's the first thing. And then we have to make sure that A and B and the carry are inside that valid range. And finally, when we return A, we also have to check whether A is actually a negative number or not. We can't just return A. We have to check if it is in the positive range, or if we actually need to invert it using bit arithmetic. So for that, we need a bit mask. And this bit mask defines all 1 bits for a 32-bit integer number. And in the beginning, we want to sanitize the inputs with like so. We're going to say A is A and the bit mask. So it means we throw all bits away that are not covered by this bit mask. And then when we compute the carry, we do the same thing. So we'll just end it with, we will end it with the bit mask. So any other bit that is outside the bit mask will be essentially deleted. And as you remember, AND means wherever both bits are set to 1, those are the bits that we keep. Right. So now let's see what we get now. And we need to handle the adding of negative numbers as well. Right. So this is accepted. What if we submit? So now we're getting an error much, much quicker. That is because we're now catching these overflow errors that occur if we allow arbitrarily large numbers. Right, so how do we deal with that? So we get an input -12 and -8. It's expected -20. However, we're getting a huge positive number. Well, that is because this number is probably outside of our range. So what we have to do, we have to add a check if A is larger or equal than. And now this is a slightly different. I had to look this actually up to figure out that this is the correct range to check for. So we changed the first F to a 7 here. Otherwise, everything I think remains the same. This becomes a 7. Yes, that's how that works. So if that is the case, it means we have an overflow within our range defined by the bit mask, and we actually need to, we need to invert a number. And the way to invert a number is you take that number and you turn it into -x -1. That is because 0 is represented, 0 in decimal form is represented as 0 bits, and 1 is represented with the 1-bit set. But how do you represent -1, right? -1 is represented with the leading 1 bit. And this is exactly what this operation does. It adds the negative, it flips the first bit. So it goes from 0 to 1, and then it subtracts 1 to make sure that we're using the full range of bits available. Right. Because we have one more. We don't have one more number in the negative, but -1 and +1, like I just showed, have almost the same representation. So this would be +1 would be like so. But in between lies the 0, which is technically speaking counted towards the positive numbers. That's why we have to subtract 1 to make sure that we get the correct value when we invert it. And by the way, if you run this operation twice, so if you do this, and then you do -1, right? You apply this operation twice, then you actually get x again. And in Python, the operation, the operator to perform this operation is tilde x, right? So for our case, what we'll have to do is, well, we have to decide what the result is. So we could return tilde and then of course our a, but we still have to flip all of the bits first. Ask. Otherwise, it's not going to be a negative number. So a slight misspoke. So -1 in decimal is represented as 1. A positive one is represented in, let's say, in binary as 0001. And -1, just to correct what I said earlier, is represented as, well, the first bit is the sign bit. And then you're flipping all of the other bits. So it would be represented like so. However, we now need to subtract 1. And then it becomes 1111 and uses that representation as well. Otherwise, this representation would not be used. Right, so that's what we do to invert a number using bit arithmetic. That's just how we do that. And otherwise, we can just return A. So if I run this now again, tests are accepted. Let's see if we can submit this. Okay, cool, and it works. So yeah, I am not sure if I really like these types of LeetCode problems. I think the takeaway really here is the trick with, turning an addition problem into a problem where you just compute the carry and the bit additions without the carry. I think that's the key idea here. And then the other insight is how to turn a positive number into a negative one in the correct, preserving the correct bit representation using tilde and XOR with the bit mask. I don't care for this type of problem so much because you have to define the bit mask and then know exactly how many bits you're going to allow. Yeah, but anyways, I guess if you know this, then you know this. Otherwise, you have to look it up.